energy is being released. If the electron is going from lower energy level to higher energy level, you have to supply energy. So one is exothermic, the other is endothermic. Energy is always conserved. In this case, using Bohr's model, we try to explain the origin of the line emission spectrum for hydrogen gas, and we can see, well, when the electron is going from level 5 back down to level 2, well, this is where you see that purple line or violet line. When it goes from number 4 to number 2, that's when you see that blue-green line. And when it goes from number 3 to number 2, that's when you see that red line. So Bohr made this proposal, and he actually did the experiment. The calculated wavelength for the frequency actually matches what we observe in the laboratory. So people are jumping up and down, and wonderful. We finally identified where does the line emission spectrum come from. We now know the basic structure of the atom there. Well, trying to understand the Bohr's proposal, the energy level or the orbits is just much like a step on the ladder. The higher you go, the higher the energy. Okay, and there is no steps in between two steps there. So it's always going to be an integer number, 1, 2, starting with step 1. There is no step 0. Okay, when you go to the first step, and that's step 1, 1, 2, 3, 4, and all the way up to infinity. Okay, and so the higher the m value, the higher the energy of the shell, if you will. You're separating the space around the positively charged center into different steps there. So each shell can be thought as a step of the ladder, on the ladder there. The higher you go, the more energy you have there. And then if the electrons is going from n equals to 1 to n equals to 5, then you have to supply a certain amount of energy, because that's not going to happen on its own. But if electron is bouncing back down from a higher energy level to a lower energy level, energy has to be released. And that's when we see the line emission spectrum. So how do we quantify the amount of energy an electron possesses at a particular step or level? Well, this is the third equation that we need you to remember. En, n stands for the number of steps, whichever step that we have here. N could be 1, 2, 3, and it's an integer number. Okay. The energy of each level is given by this equation. En equals to negative RHC over n squared. The sign of En is negative because the potential energy between the electron and the nuclear is actually, electrons are being attracted towards the center. Okay? And the energy we're talking about, and we're talking about the energy used to move the electron away from the center there. So we put a negative sign in there just to make the whole number a positive. So this equation is what we can use to calculate how much energy a particular electron has if we know where they are. If they're on step 1, step 2, step 3. Several constants involved in there. R is what we call the Rydberg constant. And again, you don't have to memorize the constant there. If we ask you to do calculation, we'll give you the constant. H is still our constant. C is the speed of light. N is what we call the quantum level of the electron, or the steps on the ladder. N equals to 1, 2, 3, 4, 5, all the way up to infinity. Okay? N is the quantum number. And later on in this chapter and next, we are going to introduce the quantum theory there. Quantum number is the main energy level. Okay? So the higher the quantum number, the higher the energy. And that's something that we will talk about a little later when we deal with the quantum numbers of electron distribution. Okay? So in this case, this particular equation, you can see the energy of a particular electron at a particular energy level. So it depends on where they are, because R, H, and C, those are constants. So the higher the energy, the higher the steps, the higher the energy. Okay, well, it's a negative number there. Okay, so in this case, we can actually calculate. Well, Niels Bohr actually did the calculation 100 years ago, and we can actually calculate the amount of energy being released if an electron is going from one particular level to another. Since En equals to negative RHC over n squared, so n plus 1 minus n. That will be the change, the energy difference between those two levels there. Okay. And for two successive levels, energy levels there, the energy difference between those two levels equals to the difference between those two energy levels there. So for E equals to 1 and E versus E equal to 2, so E2 equals to negative RHC divided by 4. E1 1 to the second power is still 1. So multiply both the numerator and denominator by 4. This E1 equals to negative 4 RHC over 4. What we're trying to do here is that we're trying to do E2 minus E1. That's the change of energy between, or the difference of the energy between those two levels. That equals to 3/4 of RHC. That's 3/4, that's 0.75. So between the first two levels there, between n equals 1 and 2, the energy difference between those two levels equals to 0.75 RHC. Between level 2 and level 3, 2 to the second power is 4, 3 to the second power is 9. And 4 and 9, the lowest common denominator is 36. And so 5 over 36, that's 0.14 RHC. So what we have discovered here is that as you go up along the energy level, and this is not your regular ladder you buy from Home Depot, each step is of equal distance. Well, the thing is, between step 1 and step 2, the difference is bigger compared to the difference between step 2 and 3. And 3 to 4, the difference is smaller than 2 and 3. So as you go up, the energy levels, energy difference between the two levels is getting smaller and smaller. Okay. Now, what we have discovered so far is that we can actually, based on our calculus, if we have electrons on level 5, moving down to level 1, moving down to level 2, we can do all those calculations. We can calculate the amount of energy that is supposed to be released by the transition of the electron going from each energy level to a lower energy level. And then that calculated value can be compared to the actual observation in the laboratory. And if we see a red line, you have a calculated wavelength somewhere in the red region, then there's a match. Okay, so in this case, we want to give you some definitions, some key terms and vocabulary. Ground state. Ground state is the lowest energy level. The lowest energy level, n equals 1. Okay. Excited state. Anything beyond n equals 1 is the excited state. Absorption happens when an electron moves from a lower energy level to a higher energy level, meaning you have to supply energy in order for the electron to go up. And then emission happens when the electron moves from a higher energy level back down to a lower energy level, any lower energy level. Okay? So the emission is accompanied by the release of radiation. That's where when we see those line emission spectrum there. And that's an indication electrons are coming down to a lower energy level, and different elements, the atoms of different elements there, they have a unique pattern of the line emission spectrum. So in the Bohr's energy level